Good day, folks. If you're wondering what Fibonacci sequence is, now is your time to understand what what is Fibonacci sequence. So the Fibonacci sequence is a set of integers or the Fibonacci numbers that starts with a zero, followed by one, then by another one, and then by a series of steadily increasing number. The sequence follows the rules that each number is equal to the sum of the preceding number. So Fibonacci sequence. Each term starts with the third, adheres to the prescribed formula. For example, the seventh number, 8, is preceded by 3 and 5, which adds up to 8. The sequence can theoretically continue to infinity using the same formula for each new number. Some resources show the Fibonacci sequence starting with 1 instead of a 0, but this is fairly uncommon. So next is, so this is the example of it. Um, it starts with a 0. The next is 1, so 0 plus 1, the next number would be 1 in the sequence. Then 1 plus 1 is 2, and 1 plus 2 is 3, and so on and so forth. So that's how Fibonacci sequence work. The histories of Fibonacci sequence. The Fibonacci sequence is named for Leonardo Pisano, also known as Fibonacci, an Italian mathematician who lived from 1170 to 1250. His story began in Pisa, so Italy, in the year 1202. Leonardo Pisano Bigolo was a young man in his 20s, a member of an important trading family in Pisa. In his travels throughout the Middle East, he was captivated by the mathematical ideas that had come west from India through the Arabic countries. When he returned to Pisa, he published these ideas in a book on mathematics called Liber Abaci, which became a landmark in Europe. So Leonardo had since come to be known as Fibonacci, became the most celebrated mathematician in the Middle East. So that is the story of Fibonacci. Fibonacci considered the sequence to be an answer of the following question. So this question, you shall remember it. So for later on, we will answer that. So if a pair of rabbits is placed in an enclosed area, how many rabbits will be born there if we assume that every month a pair of rabbits produce another pair, and that rabbit begin to bear a young 2 months after their birth? Okay, this is how we calculate the Fibonacci sequence. So Fibonacci is defined by the recursive relation defined by the equation. So f sub n is equals to f sub n minus 1 plus f sub n minus 2, where f sub n is the Fibonacci number and f sub n minus 1 is the number between f sub n, and f sub n minus 2 is the number before f sub n minus 1. This is a table representing our first term, second term, third term, up to fourth term in our Fibonacci sequence. This is just the same as the sequence I've showed earlier. This is just to emphasize. So, from the question of the rabbit, so if it only bears young after 2 months, so from December to January, it bears one pair. So since there are two rabbits now, it can 2 plus 1 would be 3, and 3 plus 2 would be 5, and 5 plus 3 would be 8. That is from the formula of Fibonacci that I've said or discussed in the previous slide. The next is, what is Binet's formula? Binet's formula is an explicit formula used to find the nth term of Fibonacci sequence. It is so named because it was derived by mathematician Jacques Philippe Marie of Binet through it was already though it was already known by Abraham de Moivre. This is the Binet's formula. Actually, there is a minus 1 square root of 5 over 2 open equals parentheses and all over um, square root of 5. But this is just the simpler form where you can round it off to remove the decimal to make it a whole number. So there are also, don't worry because later on we're gonna utilize those formulas so that you could fully understand how does it works and how do Fibonacci works. So let's just continue with this. So Fibonacci sequence properties. The properties of the Fibonacci sequence are given as follows. So Fibonacci numbers are related to the golden ratio. In mathematics, two quantities are said to be in golden ratio if the ratio is equal to the ratio of the sum of the larger of the two quantities. It is commonly found in nature and also in mathematics, design, geometry, and etc. The ratio of any two successive Fibonacci numbers is close to the golden ratio, which is approximately equal to 1.6183 and 4. Any Fibonacci number can be calculated using golden ratio. The ratio of consecutive Fibonacci term is given below. This is an example of it. Diba? Um, it it actually gives off 1.6, same as the golden ratio. This is the example how you can calculate the next term using the golden ratio. For example, 8 is the sixth term in the sequence. To find the seventh term, we multiply 8 by the golden ratio. 8 times 1.618034 is equals to 12.94427, or if we round it up, it results to 13. So the term of Fibonacci sequence below 0 can also be calculated by this formula. See, the Fibonacci number spiral, which is also related to the golden ratio. So Fibonacci number can also be used to define spiral and are of interest of biologists and physicists because they are frequently observed in various natural objects and phenomena. The branching pattern in trees and leaves, for example, and the distribution of seeds in a raspberry reflect the Fibonacci sequence. The Fibonacci sequence is often associated with golden ratio, a proportion roughly 1 is to 1.6 that occurs frequently throughout the natural world and is applied across many areas of human endeavor. Both Fibonacci sequence and golden ratios are used to guide designs for architecture, website, and user interface, among the other things. So that is the real life application of Fibonacci sequence. So now we are down to our examples and solutions part. So I'm just going to change my brush real quick. Mm. So the example one, if what is f sub 7 in the sequence if f sub 1 is equals to 1 and f sub 2 is 1.5. So we can write it down as this formula that we've seen earlier. Next is the f sub 4. So we're just gonna copy 2.5 since this is the f3. So in this part, n minus 1. So if this is the n is 4, so it became f3. So yeah, copy that, and f sub 2, which is 1.5, copy. So f sub 4 is equals to 4. Next is f sub 5 is equals to 4 plus 2.5 is equals to 6.5, plus 6 is equals to 6.5, plus 4 is equals to 10.5, and lastly f7 is equals to 10.5 plus 6.5. Therefore f7 is equals to 17. So this is how you solve this using a Fibonacci sequence. Next, the example 2, the sequence is 4, 7, and find the missing term. So we can actually use this one. So Fn, which is F3, right? Since this is the missing term, so this is the first term, the second term, and the third term. Um, this is f sub 1 and f sub 2, so therefore we're going to write it as 7 plus 4. So f3 is equals to 11. Or we can derive the formula of Fibonacci. So f n is equals to f minus n minus 1 plus f n minus 2. So, the missing is 3. And we're gonna use 18. So f3 is the missing. Since we have f4, actually, we're gonna change this to 4. And the missing is f sub 3 plus, we have 2 here, f sub 2. Yeah. So we write down 18 is equals to f3 plus um, f2, which is 7. Then change it to this 18. This became a negative, so it still results to the same number, which is 11. So that's the answer of it, 11. Like examples, the sequence starts with 1, 1. What is the next number? So this is actually an easier um, problems. We're just gonna take this 2. So f that's f3 plus f2 is equals to f4, since next is f4. So f4 is equals to 2 plus 1 plus 1. So f4 is equals to 3. That is the answer. Next question, example 4. Write the first 7 terms of the sequence starting with 3 and 4. So if our f1 is 3 and our f2 is 4, so we're gonna find the first 7 terms of the sequence. So this is the first term, we have the second term. So we're gonna find the 5 terms. So starts with f3 equals f2 plus f1. f3 is equals to 4 plus 3. f3 is equals to 7. Next is f4 is equals to 7 plus 4. f4 is equals to 11. f5 is equals to 11 plus 7. f5 is equals to 18. So we need 2 more. So f6 is equals to copy 18 plus 11 from the previous. So f6 is equals to, that's 9, that's 29. And this is the last one. So f7 is equals to 29 plus 18. 7 is equals to 9. 8 plus 9 is 7. 1. That's 4. 47. So the sequence would be 3, 4, 7, 11, 18, 29, and 47. So that's the sequence. So we have first term, our second term, our third term, our fourth term, our fifth term, sixth term, and seventh term. Next question. So find the 10th term of the Fibonacci sequence. So since this starts with 1, we can actually use the Binet or Binet's formula. So it goes like 1 plus square root of 5 over 2 raised to, we're looking for the 10th term, right? Raised to 10 because that's n. Since this is the 10th term, so we're gonna go with 10 all over 5. And we're gonna write this inclusion here, simplifying to round it up to the nearest um, tends to remove this decimal places. So f10 is equals to that's 1.6183389 all raised to 10 over 5. So f10 is equals to copy 122.9918694 over 5. So f10 is equals to 55.00036 or f10 is equals to 55. Next, example 6, the 25 term. So that's the same as the last problem. So we're just gonna use calculator if you want. Just write down the formula. So this one plus square root of 5 all over 2 raised to the 25th term all over square root of 5. So that would be f25 is equals to um 1 plus square root of 5 over 2 raised to 25, right? Raised to 25 all over square root of 5. So this results to 75025. So that's the answer. So, gimana ka? So to break this down, I'm just gonna write this. So that's from the previous slide. That's actually one point I 122.9918694 raised to 25 to 5. So using our calculator, 122.9918694 raised to 25 is equals to 17656 1.7656 to 72139. So it's written in scientific notation all over square root of 5. That gives us this value. Next is find the 12th term of the Fibonacci sequence if the 10th and 11th terms are 34 and 55. So first we're going to find the F12. It's equals to F12 minus 1 plus F12 minus 2 equals to F11 plus F10, which is 34 plus 55 is equals to 989. That's the answer for. Next is calculate the value of the 12th and the 13th term of the Fibonacci given the 9th and 10th term of the sequence. So F9 is equals to 21 and F10 is equals to 34. So F11 is equals to F9, F10 rather, plus F9. So substitute 34 plus 21 is equals to 5, that's 55, and F12. So now we're gonna is F11 plus F10. So F12 is equals to 55 plus 34 is equals to 989, and F13 is 89, or F12 plus F11, or 89 plus 55 is equals to 144. So F12 is equals to 89 and F13 is 144. If the sixth term in the Fibonacci series is 610, find the next term of the sequence. So we can actually use the golden ratio in this, since the only thing that is given is a 16th term, and we don't have any other idea what is the next or the other terms after or before the 16th term. So we're gonna write this as 610 multiplied to the golden ratio, which is 1.618034 is equals to, so this would be our 17th term, no? So F7. So F7 is equals to 987. That's Then the last is find the 32nd term of the Fibonacci sequence. 1 is to 1, 2, 3, 4, 5. So we can still use the Bennett's formula written as this one. Since we are looking for the 32nd term, we're gonna write 32 in our n and put the square root of 5. And don't forget this 2 here, and then write F32. So F32 is equals to that, same as that's 1.9918694 raised to 32 all over square root of 5 is 1, and this would result to F32 is equals to uh, is equals to 2178309, and that's the end of our discussion. Thank you for listening and watching.